Hello guys, welcome to our class. Today we are looking at vibration in open and closed pipes, and just as we discussed for vibration in strings, that is exactly what we're also going to discuss in vibration in closed and open pipes. Is that okay? So if you have your writing materials ready, please just get ready. But before then, please, if you are not subscribed to this channel, please click on the subscribe button, click on the notification bell so that whenever we upload a new video, YouTube will notify you. You can reach us via the WhatsApp number that is showing right on your screen. And then if you have any challenge, you can discuss with us or just type it and send. We'll see how to get back to you and help you in any challenge that you have. So if you are preparing for any of these external examinations, we are here to assist you and to help you. Alright, so as I said, we are looking at vibrations in open and closed pipes for today. And so if you have your writing materials ready, let's go straight to our class. You are welcome. So vibration in open and closed pipes. If you have a closed pipe, okay, the air in the closed pipe can be set into vibration. Okay, it can be set into vibration, maybe by you bringing a vibrating turning fork close to the open end of the closed pipe. So for a closed pipe, just like we did for a vibrating string, we can actually find the first harmonic or the fundamental frequency, the first overtone or the second overtone, the way we did for a string. So for a closed pipe, when an air column vibrates in a closed pipe, a node is always formed at the closed end, while an antinode is always formed at the open end. And that is exactly what we have here. This is fundamental frequency. There is a node at the closed end, there is an antinode at the open end. Then this is a node, this is a node, this is an antinode, open end. This a node, this a node, this a node, and this is an antinode. Is that okay? So as we did for a stress string, that's exactly what we're going to do for vibration in closed pipes. So if you look at this, you find out that the length of this pipe is equals to, for the first harmonic or fundamental frequency, the length of the pipe is equals to 1/4 of a wavelength. So as we did for the pipe, we have that wavelength is equals to 4 times L. Then from our wave equation, lambda F, V is equals to lambda F. So fundamental frequency for a closed pipe, is equal to V all over 4L. This is the fundamental frequency for a closed pipe. V all over 4L, that's F0, first harmonic, is equals to V all over 4L. Okay, so this is what we have here. Then for the first overtone or second harmonic, we see that for the first overtone, second harmonic, the length of the pipe is equals to 3 all over 4 of the wavelength. Okay, so that's what we're going to do in our next slide. So for the first overtone, we see that L is equals to 3 all over 4 of wavelength. So which gives you that wavelength is equals to 4L over 3, right? So if you follow your equation, V is equals to lambda F, and that F is equals to V all over lambda. Then to give that F1, which is first overtone, is equals to V all over 4L divided by 1 over 3. So if you work this out, you have that F1 is equals to 3V all over 4L. 3V all over 4L. So this shows that the first overtone of a vibrating open or a closed pipe, first overtone is equals to 3 times the fundamental frequency, and that is exactly what we have here. It's equals to 3 times the fundamental frequency. Is that okay? It's 3 times fundamental frequency. Then for the second overtone or third harmonic, for the second overtone or third harmonic, the length is the number of wavelengths here is equals to 3, is equals to 5 over 4 of 5 over, the length is equals to 5 over 4 of the wavelengths. So as we did for the other one before, you had that 4L, if you cross multiply, is equals to 5 lambdas, and that lambda is equals to 4L all over 5. So from V is equals to lambda F, F2 will be equals to V over lambda. So if you substitute for lambda here, you are going to have that F2 is equals to 5V over 4L. So what that simply means that F2 is equals to 5F0. So, and that is what we have here too. Okay, that is exactly what we have here. So F2 or second overtone is equal to 5 times the fundamental frequency. 5 times the fundamental frequency. Alright, so this is these are the various formulas for a vibrating closed pipe, for a pipe that is closed at one end and set, and the air in it is set into vibration. So I want to solve a problem now. This is a sample question that I want us to just consider. The question says that a pipe closed at one end is 100 centimeters long. If the air in the pipe is set in vibration and a fundamental note is produced, calculate the frequency of the notes. Velocity of sound in air is 340 meters per second. Okay, so for this particular pipe, you are given that the length is equals to 100 centimeters, which is equals to 1 meters. Now, for a vibrating fork that is producing a fundamental note, the frequency is equal to the frequency for a fundamental is equals to V all over 4L. So if you substitute all those information into this equation, you will have your answer readily. So V is given to you to be 340 divided by 4 multiplied by 1. So if you multiply this out, you are going to have 85.0 Hz as your final answer. Okay, so this is how to solve some of the problems that you get from this. Okay, so that is that. Let's see if we can solve another problem. So this one is another question that we need to also consider. says that if the fundamental frequency of a closed pipe organ on a D when the speed of sound is 340 is 170 Hz, then the length of the pipe is what? For this particular question, they mention fundamental frequency. So from here, what you are looking for is the length. Okay, you are looking for length. So here you are be giving V to be equals to 340 meters per second. You are be giving F to be equals to 170 Hz. And then you know that for a closed pipe, the fundamental frequency is given to be V all over 4L. That's the fundamental frequency, V all over 4L. So if you substitute into this equation and then make L your subject of formula, you will have that 170 is equals to 340 divided by 4 times L. Okay, so if you do the mathematics, so by the time you make L your subject of formula, you will have that L will equals to 340 divided by 170 times 4. So if you work this out, this will give you 0.5 meters as length, or is equals to 50 centimeters as the case may be. Okay, so just understand how to use each of the equation and then your answers will come out readily. This is a jam question. Okay, so now let's go to open pipes. We've discussed closed pipes, so let's discuss open pipes very quickly. So for open pipes, if you look at the equations for open pipes, they are just like the equations for vibration in string. So in this particular one, I'm not going to waste too much time on it, because if you understand the equations for vibrating string, this one is exactly the same thing. So for an open pipe, when a stationary wave is formed on an open pipe, you have two antinodes at the open ends, then a node at the center. Okay, so you have two antinodes at the open and then a node at the center, and that is what you have in these three cases. This is the first harmonic, second harmonic, third harmonic, and this is your fundamental node, first overtone, second overtone. So for the fundamental nodes, the length of the pipe, the length of the wave produced equals to half of lambda. So, and you remember that your lambda will be equals to 2a, just as we have for fundamental node for stress string. And then from V is equals to lambda F, and F0 is equals to V over lambda. Then when you substitute, you have that F0 is equals to V over 2a. Go and check the video on stress string. You see that this equation is exactly the same. So which means that your fundamental frequency for an open pipe is equals to V over 2A. Okay, so check that video, and then everything that we did there, you can just apply them here. This is equal to half of a wavelength. Then here, this distance is equals to 1 wavelength. Okay, so this is your fundamental note and your first harmonic. For the second harmonic, right, this is your second harmonic and your first overtone. for the second harmonic, the length is equals to one wavelength. So if you work out the way we did for vibration in string, you find out for the second harmonic, F1 is equals to V all over L. So which means F1 is equals to 2F0. Okay, F1 is equals to 2F0. So I don't know wasting much time because we have treated this one already in vibration in string. So if you understand that one, just go and watch that video and then compare with this one. Everything there is exactly with vibration in open pipe. Okay, then this is for first overtone. Then for second overtone, which is this, the length of the pipe is equals to 3 over 2 of the wavelength. So wavelength is equals to 2L all over 3. Now V is equals to lambda F, and F2 second overtone is equals to V over lambda. Then when you substitute this lambda into this equation, to give you 3V all over 2A. So, and this means that F2 is equals to 3F0. I've said compare this with that, the one we treated on string, so that everything is exactly the same thing. There's no difference. So guys, this is it. We are going straight to some questions that we need to take care of. So let's go. Alright, so this is a sample question. An organ pipe of length 40 centimeter open at both ends. Sound is fundamental note. Neglecting end corrections, calculate the frequency of the notes. Speed of sound in air is 340 meters per second. So here you are be giving the length to be equals to 40 centimeters, which is equals to 0.4 meters. You are giving velocity to be 340 meter per second. So if the organ sounds is fundamental note, it means that the frequency of the fundamental note is equals to V all over 2L. So substituting into this equation, we have 340 all over 2 times 0.4. So work that out. If you work that out, we'll get your frequency to be equals to 425 hertz. See, so you're only just to understand which of the notes or which overtone or which of the note is the musical instrument producing. Is it fundamental? Is it second harmonic or third harmonic, or is it first overtone or second overtone? That will guide you on which of these equations to use to solve your problems. Okay, so let's go on. Okay, so this is your test your understanding page. Thank you so much for your time. If you look at all these questions, they are just about all that we have discussed, right? So go through these questions and then solve them. Anyone you have any challenge, let us know. Check your textbooks, check your past questions. You will see questions like this to solve. So thank you so much, and I think this should be the last topic the last class for sound waves and introduction to wave. So in our next class, we are going to be discussing light wave. So thank you so much. We appreciate you. Please, if you have not subscribed to our channel, please subscribe to the channel. Click on the notification bell so that whenever we upload a new video, YouTube will notify you. This is Normal Science Tutors Online. We appreciate you for your time. Give us a thumbs up, give us a like so that you continue to encourage us. Reach us through the WhatsApp number that is showing on your screen. Thanks, and we hope to see you in our next class. Please invite your friends too.